And then also just like a clarifying question.
Yeah,
So when if it's in parentheses and it's A plus B and then outside of parentheses is star closure, does that mean it can be A and B too, or is that?
yeah, you're picking A or B any number of times. So you can think of the first selection. I'm not going to pick anything, and that way it's zero. 0 times you've done this. The first time you're picking A or B, and that goes in the first position. The second pass, you're picking A or B. Third time you're picking A or B, and you're concatenating all of those selections together. What are all the legal selections that you could make, stopping at any time?
So would it like a valid string be A, B, A, B?
Yeah. On pass 1, you pick A. On pass 2, you pick B. On pass 3, you pick A. On pass 4, you pick B. And since 4 is something that is 0 or more, that is legal. All right. We're gonna dive back into everyone's favorite pumping lemma. We introduced this concept at the end of last class, and that was certainly a thing that happened. So the basic idea is that we're going to start to think of DFAs instead of as particular DFAs representing a particular language. Now we're going through the proof type for how we show a language is not regular. We're going to do that by taking a language that isn't regular, and we're going to assume that it is. Assuming that it is, we know we can construct a finite DFA for it, some finite number of states. And then the goal of this is to derive a contradiction, to show that if such a DFA were possible, it would be able to produce this particular string that is not in the language, and it would have to be able to produce this string by its construction. So let's dive into and look at a couple of properties of DFAs as part of motivating this whole discussion, because I want it to be as intuitive as possible. So the first is, you can imagine a DFA that does not have any cycles in it. If there is no way to get from a state to another state, then the language that that DFA accepts must be finite. Can anyone expand on that? According to your intuition, why is that true?
Well, if you were to think of it like as like a loop, like a dollar or something, then it wouldn't be an infinite loop because there's no way to just keep going around.
Right. So we know that there are, one, a finite number of states. There are a finite number of transitions, which means there are a finite number of simple paths in the graph. If you don't have some loop in your graph, then there are a finite number of simple paths. If there are a finite number of simple paths, then the language that it accepts has to be finite. You can't produce an infinite number of paths through the graph because you can't get back to where you started and iterate that loop an arbitrary number of times. As soon as you have a loop, you can iterate that loop an arbitrary number of times, and that's what explodes that language from finite to infinite, because you can now iterate that loop 0 times, 1 time, 2 times, 3 times, 1,000,000 times, 7 nonillion times, doesn't matter. So if there is a cycle with a non-empty label, meaning that it includes at least one character in the input to do so. So we can't count lambda transitions as part of this in an NFA. But again, we're still talking about DFAs, so as long as we're consuming a character throughout that cycle, then the language is infinite. Because we can iterate that cycle any positive integer number of times. There are an infinite number of positive integers, you'll get a different string for each number of times that you iterate that loop. Let me draw that out, just so that we can get a sense of what that looks like. I'm feeling red today. I'll do this as simply as possible. We have Q0. It's final, and it loops to itself on an A. There's a loop. What are the strings in this language? Lambda, A. You can see that each time you iterate the cycle, you're just adding an A to the past string of the number of iterations you had the last time. You iterate this twice, you iterate it a third time, you add an A to the end of the 2 A's from iterating it twice. So you don't need a complicated DFA necessarily to see that this is the case, but you can expand this to an arbitrarily large DFA and an arbitrarily large loop across some number of states that isn't just a self edge like this. But it goes from, if this didn't have a loop, like for instance, this A leads to a final state that is Q1, and this is not final and doesn't have a self edge. Now you can see that, what language does this accept? A, the single string A. That's it. If there are no loops, then this can't go back here. This could go an arbitrary number of places, and that just tells you how many strings there are of length 1 in the language. As soon as you look simple paths of length 2 from here, since none of these can go back to each other, that would create a loop, then all the simple paths of length 2 describe all of these strings of length 2 that are in the language. All the simple paths of length 3, but since this is finite, there are a finite number of states. That tells you, one, the longest string that's in the language. It doesn't accept strings that are longer than that, because that's the longest simple path we can iterate in this finite graph. So it tells you that the language that's accepted is finite.
If the language is finite, it is regular.
Yes.
Is the converse true, where if it is infinite, it has to be regular?
There were many instances of infinite languages that were regular. But yeah, if it is finite, then it is regular. So every infinite regular language has a DFA with a cycle. That's the conclusion that we can draw from this. So in order for a question, is this language regular? In order for that to be interesting, the language must be infinite. Because if it's finite, it's obviously regular. But if it's infinite, now the question is it an infinite regular language or an infinite non-regular language? If it's an infinite regular language, then there is a finite DFA with at least one loop in it. Or one cycle. We're going to call it a cycle. We can skip that cycle, meaning we iterate that cycle 0 times, or we can iterate that cycle an arbitrary number of times. And no matter how many times we iterate it, we'll generate, if it's a different number of iterations, we'll generate a different set of strings that are in the language. We are going to start labeling some variables in this to give you a sense of, we're going to break this generic DFA down into 3 main components. So before we dive into the exact 3 main components, we're going to talk about, all right, the cycle has a label. We're going to call that B. And some string that we're going to call W1, W2 is a sentence in this language that the DFA accepts. We're going to say W1 represents the path to get to the cycle from the start state. So from the starting state to the beginning of that cycle. That may be empty. In the DFA that I just drew of one vertex with a self edge, one state with a self edge, then that meant that the getting to the cycle was empty. There were 0 states that we needed to, 0 edges we needed to transition from in order to get to the start of that cycle. W2, the path from the cycle to the final state. So we could then say that any string in this language could be represented as W1 V star W2, where we could omit the V. We can include it once, we can include it twice, we can include it 3 times, an arbitrary number of times. This says that all of those strings are in the language because each of these end in a final state. Do we buy that? Does that concept make sense? Do we feel like that's true? I'll draw out an example of this. So we have a starting state. We have some process, we get to some state that is the beginning of some cycle. And via that cycle, we're going to end up either back at this state or at some other state. And then we're going to get to some final state. So this path is what we're calling W1. This cycle is what we're calling V, and this path is what we're calling W2. So do we agree that there exists a path W1, W2 that ends in a final state? Yes. Do we agree that there exists a path W1, V, W2 that ends in a final state? Yes. W1, V, V, W2 ends in a final state, etc. for an arbitrary number of iterations of this cycle V. We're actually going to rename this here quite soon because no one really likes W1 and W2. So I'm going to call this X, I'm going to call this Y, and I'm going to call this Z. So you can name this whatever you think makes sense, but the W1 and W2 are meant to be paths that are iterated once, and the V is meant to be a path that is iterated an arbitrary number of times. Questions on that concept? All right, now we're going to break into all of what we're going to need to know to be able to construct this proof. So we're going to make an assumption. The DFA has M states. Even though I introduce this, and I'm going to introduce this in a second as a game, the game is played with finite numbers, but the proof is constructed with variables. I'm just going to put that out there right now because I see lots of proofs in this class where someone instantiates a variable with a particular number and then says, see, it works out, and we cannot have that happen. So whenever you see a letter or variable, I'm representing something that you should think about as a proof. When I talk to you about this as a game, you can imagine this is just being played as a way to understand how this process works. The way that you play the game is not the way that you go about proving it in general. So we're going to say that the DFA that accepts this language that we want to show that is not regular has M states. Great. We know that we're going to encounter the cycle by the time we've read the first M symbols in the input string. Why is that? Yeah.
Because then you would have revisited every state.
Every possible state. Yeah, so let's say this DFA has 10 states, and you can think of 10's a lot, 5 states. And we're gonna envision these states as being in a line, regardless of what happens. So we read the first character, we transition from this state to that state. We read the second character, we have a couple of options. We can go to a state that we haven't seen before, or we can go to a state that we have seen before. If we go to a state that we have seen before, that's a cycle. So we have to go to a state that we haven't seen before in order to keep from having this cycle. When we're here, we consume a character. We either go to a state that we haven't seen before, or we go to a state that we have seen before. If we go to a state that we have seen before, we create some kind of cycle. So by the time we've read M symbols, 1, 2, 3, 4, it's really even M minus 1, but by the time we've read M symbols, we know that we've reached that loop. If this language is infinite, then in this DFA of M states that I've instantiated to be 5 in this case, by the time we've read the first 5 characters in the input string, we know we've reached the start of some loop, assuming this language is infinite. Does that make sense? How do we feel about that?
Is this kind of where like the pigeonhole
Yeah.
thing comes in?
Yeah, so we know that when we read that 6th character, we are either in a loop, we would have at least gotten to the loop. We have to have gotten to the loop. This turns out to be instrumental to this proof type. So a very important component of this proof is this intuitive idea. You've read M characters, you've reached the loop. If you have not done that at that point, then your language has to be finite. So now we can start to what we're going to call pump this idea. If we can generate a string XZ or XYZ that iterates this loop once, we can now pump this. If we can identify every possible place in the first M characters where we could have started this loop, then we could say if we expand this to an arbitrary number of iterations of this loop, can we generate something that's not in the language? So that's the concept of the pumping lemma. All of the work that we need to do intuitively to build up this idea of the proof that we need to construct. So this is a great time to ask questions if any of this preliminary work is even remotely fuzzy, because we're going to be using it all logically to construct this proof type.
When you're saying that it does not adhere, you're saying that it passes the DFA.
It's,
It isn't in the language.
yeah, basically we're saying if we have this path to a loop, iterate a loop, going to an end. If there's a single string that we can create, that if we can say, all right, we can identify what W1 is, we can identify what V is, we can identify what W2 is. For any possible V, I can create some number of V's where this string is not in the language. So every possible V we're going to have to look at, but for each V, we produce a single example of some string when pumped some number of times that is not in the language. If we can state that, then we have proven that this language is not regular. Does that make logical sense? I think it'll make a lot more sense when we see it in practice, but what's most important at this stage is this intuition. Everything that's on these first couple of slides that we've gone over. You understand that, this proof type can make sense. You don't understand this, it's going to be hopeless. Or we'll have to start back over at it at some point. No more questions? All right, let's dive into the actual proof logic. All right, we always start by saying something like, let L be an infinite regular language. There exists some positive integer m such that any string in that language with that length of the string greater than or equal to the number of states in the associated DFA that represents it, we can decompose that string, W, into three components, X, Y, and Z. There are two additional rules that need to be followed to adhere to the intuition that we just covered. The first rule is that the length of XY must be less than or equal to M. This is saying that getting to the loop and completing the loop has to happen within the first M characters. Do we buy that from the drawing that I made from before? 5 states. By the time we read 5 characters, we've gone back to some state that we visited before. 1, 2, 3, 4, the first 4 of those can be all new states. By the time we read that 5th character, we're going back to some state we've seen before. But again, we're just talking about this in general, where X is getting to the loop, Y is iterating the loop, getting back to somewhere you've been before. That length must be less than or equal to the number of states in the associated DFA. The second very important rule is the length of that loop has to be at least 1 character. So we can't have a loop that consumes no characters. These 2 rules are all you need, but they are also very important. We can now say we can produce an arbitrary number of strings in this language by pumping the loop. We can now create W sub 0 by iterating this loop 0 times. W sub 1, iterating this loop once. W sub 2, iterating this loop twice. W sub 3, iterating this loop 3 times. And this will produce an infinite number of strings that are all in the language. Again, assuming that it's regular. Questions on any of this notation or what any of this means compared to what we just saw? I want to make sure I take my time here because this all comes together in one big idea. So if you have questions, make sure to ask them. Yeah.
Can you just explain WI again?
Yeah. So maybe I'll give you an example and draw this out. So let's give you Q0, Q1, then loop to itself and go to a final state Q2. I want this to be as reasonably simple as possible with each of these components having some value. So this is going to be A and B and A. So strings that start and end with a single A that have an arbitrary number of B's in the middle of it. So if we're looking at this, we know that since this DFA has 3 states, by the time we read the first 3 characters, we must have entered the loop and completed the loop. 1, 2, done. That would have to be the case. It would be 3 if the loop were on the final state. But that is the maximum allowable number of characters read before we've completed the first pass of the loop. So if we wanted to create a list of strings in this language in terms of X and Y and Z, what would they be? A string in this language is AA. That is W sub what? 0. Yeah, this is W sub 0 because we iterated this loop 0 times. If we wanted to make W sub 1, we'd iterate the loop once, and that would be A, B, A. We know that for any string in this language, we have to traverse X to get to the loop. We have to traverse Z to get from the loop to the final state. Draw an arrow here. But you can see that this creates W2 onward forever. That is the worst W I've ever drawn in my life. And this produces an infinite number of strings in this language. And this will be the case for any DFA over any infinite regular language, is that we can break it down into getting to the loop, iterating the loop, and getting to the final state from the loop.
So that WI is basically just saying how many times it goes through the cycle.
Yep. So we're defining, yeah, each W in terms of the number, the subscript of the W is the number of times that we iterate this loop. This I represents that I, same number of times. Any questions on that? Everything good for on the board? All right, so that's what that notation means. We can say all of those are in the language for all I greater than or equal to 0. Every one of those W sub I strings is a sentence in this language. This tells us that any string that is at least length M in the language can be broken down into those 3 parts as well. There is no string in this language that does not adhere to this concept. It's either shorter than M and reaches a final state before it's had a chance to loop, or if it's longer than M, there is a loop somewhere in that DFA that it traversed. So this is the logic that we will use to prove that a language isn't regular. Now, the challenge is in making this complete. Because what's Y? That's the biggest problem. There are going to be options for what Y could be. Since this is an arbitrary DFA, we're not looking at a particular DFA example when we make this, because we're using this to prove that our language is not regular, which means the DFA doesn't exist. You can't tie yourself to an image to look at it because it doesn't exist. We need to show that no such DFA exists. So to do that, we need to look at all possible values of where this loop could be and show that if the loop could be in any of those places, we pump it some number of times, 0 or greater, and we get some string based on the definition of what Y is or what XY is that produces something that is not in the defined language. So the pumping lemma refers to this concept of repeating Y some number of times. So the goal is to identify a value of I such that X, Y to the I, Z is not in the language for every possible Y, such that we adhere to these constraints. And that means that there are a finite number of what Y could be because it has to appear within the first M characters. To try to make this a little bit more intuitive, I hesitate to do this because I've seen it throw people off, so I'm trying to explain it better this time. So I'm gonna see if this confuses people or not. Hopefully it doesn't. But you can imagine playing this as a game. In terms of how you write your proofs, throw all of this out. This is just to make, yeah. Everyone's just like, nope. I like it. So you can phrase it as a game between two players. Player one instantiates M. Says that I will assert that a DFA with 12 states exists to represent this language. Player two takes that value of M and says, okay, I'm going to pick a string that is in the language. So you have to pick something that's in the language of length greater than or equal to this value that player one picked. And that's going to become the basis for this game. Player one then chooses the decomposition of XYZ, making life as hard as possible for player two, but adhering to both of those rules on the prior slide. The length of XY has to be less than or equal to M, and the length of the loop has to be greater than or equal to 1 character. If you do this right, player two is going to have as hard a time as possible. But if the language is not regular, there is no decomposition that you can pick that player two won't be able to find an example for. Then player two picks the value of I such that when you pump the string, it's not in the language. If they're able to do this, player two wins. Of course, for a proof, we have to show that for any value of M, not some instantiated value of M, we have to show it for any value of M, no matter where we pick the decomposition XYZ, we can pump a string somewhere that shows that that's not in the language. That's what we need to do for the proof. But at least thinking about it as a game allows you to engage with the process. The process of at least interacting with it, not the process of proving. Do we see how this is more of an example rather than a proof? That's the really important distinction here. This gets you an example. It says, great, no DFA exists for value M less than this, given what player one picked. We would have to look over every possibility that player one could pick to be able to show that no DFA of size, whatever player one picked here or less, is possible. That says nothing about DFAs of larger values, which is why we can't instantiate this value when we go through the proof. We have to say no DFA of an arbitrary but finite number of states could exist. Yeah, so this is the really important part here. If it is possible for player two to win the game, then the language is not regular. So in all possible ways to play this game, if it is impossible for player one to win the game, then the language is not regular. So that's the proof we have to go through, is that player one cannot win this game, no matter how they play.
You're playing this for every string length and then every iteration. Like,
Well, you can use M for the string length.
Mhm.
You can say, I can find something. So let's say, for instance, the first example we're going to go through is the language that we've seen already, A to the N, B to the N. Instead of picking a value for M, we're going to state that the string that we're going to pick of length greater than or equal to M is A to the M, B to the M. And now whatever player one picks, we're picking the string of whatever they pick for M. They pick 20, we're going to pick the string A to the 20, B to the 20, because its length is greater than 20. This length would be 40. The length of this is twice as long as whatever they would pick. So we are going to do this variabilized, and then everything else variabilized as well. But the game is kind of how to instantiate it so that it's less abstract and obfuscated. That's why I wrote this idea out. Yeah.
So comparing the example to the actual proof, the proof will be like player two is proving it for every single value above M.
It would be something like player one feels like they're not winning this game. Player one needs to now go prove that they can't win this game and it's horribly unfair.
So they're proving, yeah.
Yeah. They're proving that no matter what I do, player two can beat me. It's like tic-tac-toe and going first. If there were no possible cats games, the player who goes second, if you play well, cannot win tic-tac-toe against an intelligent player or someone who plays perfectly. Very similar. You would go through the proof to say, well, as player two, I'm playing an AI that has learned how to play this. I can't win this game. You can't prove that by playing the game. You've lost 1,000 times in a row. It's still not a proof. You need to go through and find the logic of why, no matter how many times I play this game, I will never win with any strategy. All right, so yeah. Just because player one happens to win this does not mean that the language is regular. That just means that player two sucks, potentially. Get good, player two. The language isn't regular. You should be winning this every time. Let's go through an example. I'll stop here and ask again for any questions, because again, this is vital difference between how we're going to go about this and how I like to conceptually understand it. Because my research is in games, I really like to think of as much as I can as a game. All right, so let's take a look at an example. We want a language such that we're going to have some string W followed by that same string reversed. Is that language regular? This tells you the answer is no, but we want to try to show this in some way, shape, or form. Any intuition as to why this language isn't regular?
We don't know the state of W to reverse W.
Yeah, we need to know the sequence of characters. The history matters now. We would need to store something to be able to determine that. What do we call WWR? Do we have a name for that in terms of stuff that we've seen before? It's a subset of something common that we see. A subset of palindromes. ABCBA is not in WWR, but it is a palindrome. ABBA, on the other hand, is in WWR. I guess even length palindromes. Question?
No.
All right. So how we would do this is player one picks M, and remember that in order for player two to show that player one can't win the game, we cannot construct our argument in terms of what player one picks. We have to generalize our argument to whatever player one picks for M. We're going to generate something based on what they do. So again, we're taking the role of player two. So we want to pick a string such that the first M characters are, we're going to assume that the alphabet here is A's and B's. So we want the first M characters to all be A's, because otherwise this is going to be impossible to show. So player two needs to play intelligently to win the game, but there's always a way to play intelligently if the language isn't regular. So we want WWR. We need the first M characters to be all A's, because remember, player two gets to pick the string. So player one says, I can generate a 20-state DFA that recognizes this language. And going about this, you would say, all right, you picked 20. I was going to say A to the M, B to the M. And then the rest of this backwards would be B to the M, A to the M. So we would have W, WR. But if you do this, we knew that first rule that the length of XY had to be less than or equal to M. That means that both getting to the loop and iterating the loop has to be all A's. Does it make sense why that is?
By then you've seen every state.
Yeah. So I'm gonna draw this out. Like player one picked a much smaller value because drawing out 20 states to show this, I can do that in a lot less than that. In a way that's not gonna take so long and be so confusing. But let's say they picked something like 3 states. I'll even make it 4. So we pick A, B, B, A as our string for player 2. And we would say now that with these 4 states now, within the first 1, 2, 3, how do we read that 4th A with this DFA of this size without getting back to some other state? You can't. This has to now loop back either here or here or here, or one of these states would have had to go back in some way, shape, or form to create a loop. We could not read 4 A's in a 4-state DFA without creating a loop. So doing this now, we can kind of show that, all right, well, this loop has to occur within only A's. Does it make sense now that if we pump wherever this loop happens to be, we're just generating more A's? So basically that's saying, since we can break this down into x, y to the I, z, basically we know that x and y come from somewhere in these characters, and z is here or potentially longer. So this is the minimum length of z, all of this, getting from the loop to the final state. Maybe this is our final state. So we know that x, y to the I occurs somewhere in here, and since we know the length of y has to be at least 1 character, we pump that some number of times, it's just going to generate more A's. If we do this some number of times, does it matter if the length of y is 1 or 2 or 3 or 4? It's just going to generate more and more and more A's. And if you add some A's to this, is that in the language WWR? Everything else being held the same? If we have 6 A's, 4 B's, 4 B's, 4 A's, is that in the language? No. It doesn't matter how many A's you add. As soon as you add at least 1 A, this is not in the language anymore. So regardless of the value that we picked for y, where y happens to be, because the next thing the player 1 gets to do is pick the breakdown. We have the string, and now they tell us critically, how am I going to make this not work? How can I force player 2 to not be able to prove this? They pick the breakdown of x and y. Maybe they say, this is x and this is y. X is the first A, y is the next 3 A's. So player 2 then would say, all right, well, if you do that, I'm going to pick I equals 2, and I produce A, B, not in the language. On the other hand, player 1 could have picked x is AA, and y is AA. If that's the case, you again pick I equals 2, and now instead of having 7 A's here, you have 6 A's here. Still not in the language. The last thing that player 1 could have done is pick an x that is length 3 and a y that is length 1. If you do that, you can again pick I equals 2, and now you have 5 A's, 4 B's, 4 B's, 4 A's. Still not in the language. So you show that for whatever player 1 could pick here for the breakdown of x, y, there exists some I, some number of times we're going to loop this, that produces a string that is not in the language. If we can show that player 1 cannot pick a good breakdown here in a way that player 2 loses the game, then we have shown that this language is not regular. And the only reason we were able to do this is we picked a string that was based on the length of what player 1 picked for m. We did this with 4, but if player 1 had picked 6, the string that we would have generated is a to the 6th, b to the 6th, b to the 6th, a to the 6th. If player 1 had picked m equals 10 million, we would pick a to the 10 million, b to the 10 million, b to the 10 million, a to the 10 million. It would create a ton of cases, but you can generally show that no matter what, if y is at least 1a and only comes from this first section of a's, then no matter what, you're going to generate something out of the language. This is the first point I'll check in with you. How do we feel about this process? I don't expect this to be good. Very mid to, yeah, what I would expect. This is not easy. This is the hardest thing we've covered, and it is the hardest thing to understand from scratch in this class. in my opinion. So I'm gonna give you or show you kind of this, here is the slide visual for this. We have A to the M, B to the M, B to the M, A to the M. We pick the breakdown X, Y, they come from all A's because player two intelligently chose this structure. When player one picks the number of states, player two picks the structure of the string that adheres to the language. There are many, many more WWRs than A to the M, B to the M, B to the M, A to the M. But it becomes an example that shows no matter how you break down X, Y, this concept of A to the M, B to the M, B to the M, A to the M has to be in WWR. You can't have a DFA that accepts WWR without accepting this concept. So if we show there is no way to express this concept via a DFA, then there's no way to express this concept in a DFA, because this is a larger language than that.
Is there a world where player one can throw this? Throw the game?
Oh yeah, of course. That's why going through the game is not a proof, because player one can be dumb. We need to show that it's impossible for an intelligent player one to win this game. We're going to dive into another example because we really need to see this many times in order for it to click.
Just confirm, player one is forced to pick an X and Y that are all A's because of the structure being A to the M.
Yes.
Player one needs to pick within the sample set from M.
Yes. So the important part of this game is right here. If player two does not pick an intelligent string here, the rest of this is going to fall apart. This actually becomes the hardest intuitive thing for most people to get a grasp of is, given that you see the language, how do you pick a string such that this proof is possible? Because you could pick some strings where the proof is not possible. What if I pick something like A to the M over 4, B to the M over 4, B to the M over 4, A to the M over 4? Now the first M characters is the entire string. That means that Y can be anywhere in the entire string. You pick it to be a place that's in the middle of both B's, and then you pump them on both sides, and you still get A to the M, or at least it adheres to WWR. It doesn't adhere to A to the M, B to the M, B to the M, A to the M anymore, but you pump it and it still adheres to WWR, which doesn't complete the proof. So if we're thinking about this in terms of propositional logic, then we need to say for all M, there exists some string such that for all possible XY breakdowns, there exists a string, not an L.
Yeah.
It's a long convoluted, I guess it's predicate logic. It's a long convoluted predicate logic statement, but that's what we need to show. Yeah.
So if you were trying to go about finding a W, is there like a procedural way to do that? Or would it be like you get good at doing the proof?
A lot of it is intuition.
You have a good idea. of
Yeah,
this,
there's
and
no
you
real
test it.
great algorithm for it.
Huh?
There's no real great algorithm for it. It is
So it's
something
more
we
of
do
just
know.
like a practice thing.
Yeah. Practice and intuition.
You really want to screw this guy over, why don't you just always pick an M that's like one larger or equal to whatever he picks, right?
Depends on the string type. We'll see sometimes where even that doesn't necessarily work, and you have to restrict the space of this language down into something that really won't work with a particular string type. Yeah.
Sorry, can you clarify again, like, how does when player one's picking like an X and Y, how do they lose in that case again? Picking that?
Yeah, so player two is generating some number of pumps, some number of repetitions of that loop, such that the resulting string is not in the language. So the idea is that player two picks here such that no matter what player one picks here, they can't win the game. There exists some counterexample to what they would pick. So the proof comes from, yeah, not playing the game once, but showing the player one cannot win the game. At least that's how I like to think of it.
So that how does it like player one lose in this situation again?
if they are unable to prevent player two from generating something that's not in the language. If the language is regular, then player one can always win the game. If the language is irregular, then player two can always win the game.
So player two has to always win the game or just win the game once?
We have to prove that player two always, or can always win the game, or player one cannot win the game. That is our goal with the proof. You could structure it as a game where some people could win or lose, but if you structure it as a game, the proof comes from player one can never win the game against an intelligent player two. You need to construct the argument as the intelligent player two that proves that player one can never win the game. Questions?
I guess one last question.
Yeah.
Like, in this example, player one can't win because the X and Y are just a bunch of A's and it can't be
Yeah.
A and B or something.
Yeah, player two picked this structure such that player one was restricted to picking X's and Y's that are only in this section. Regardless of what player one picks in here, player two can come up with a counterexample that produces a string that's not in WWR. Long predicate logic proof. Many parts. So let's hit the next example if we're okay with that. Anything else we can cover before we hit that next example? I guess we don't have a ton of time, but we'll introduce the example so you can think about it, have nightmares about it all weekend. All right, alphabet still A, B. The language is all strings with more B's than A's. So we'll write that down and then we'll start to get going. So the place to start, remember that we are always player two in this game. So player one chooses some M. Our task is to create a generic string such that it adheres to the language and uses M to determine what that string is. Yeah,
You do like A to the M, B to the M plus one.
okay. Yeah, there's something that says how many more B's than A's. We just need some structure. So we could do something like A to the M, B to the M plus one. That's a legal string that's in this language. And no matter what player one chooses for M, this will create something in that language that we can use as a basis for our proof. Yeah,
So then we could like set it up somehow where we pump a bunch of A's and then if there's more A's than B's.
yeah, exactly. Since we know that the length of Y is at least one A, possibly more A's, but it has to be only A's via some number of pumps, it is possible to get more A's than B's. That is exactly the intuition behind proving this language is not regular.
And you think because he has to pump it at least once, then it'll be AM plus one?
We get to pick the I. So we could even say 10 billion. No matter what we choose for the length of Y, it's going to be between 1 and M. Those are the bounding points for the length of Y. If we said, regardless of how many there are, multiply how many there are by 10 billion. Since there was only one more B than A, we're adding at least 10 billion A's to the front of this string, and some product of that, some number of 10 billion times something more A's to the front of the string. No matter what value of that we pick, there are going to be more A's than B's in the resulting string. And that by itself tells us that this language is not regular. We could not come up with any finite number of states to be able to recognize this language. Intuitively, it's also because regardless of how we are constructing this string, we need to be counting the number of A's and B's that we see. You would only really need one variable. How many more A's than B's have we seen so far? It could be positive, it could be negative, but that is a single piece of storage that a regular language doesn't allow us to have. So we'll stop there. We'll come back to it on Monday. I have office hours starting now for any homework related questions. This made absolutely no sense. Can we go over some examples types of questions? This made some sense, but I really want to understand it better types of questions. Whatever's on your mind. Have a good weekend.
Have a good weekend too.